Its daily motion, too, is found to agree very closely with the predicted, and judging from the last circumstance, the planet's distance, as stated above, must be nearly the truth. Thus, the result of these calculations was the discovery of a new planet in the place assigned to it by theory, whose mass, distance, position in the heavens, and orbit it describes around the sun were all approximately determined before the planet had ever been seen, and all agrees with observations so far as can at present be determined. It is found to have a disk, and its diameter cannot be much less than 40,000 miles, and may be more. Its motions are very slow. It is at present in the constellation of Aquarius, as indicated by theory, and it will be in the constellation of Capricornus all the year 1847. It may be readily seen in the telescope of moderate power. Whatever view we take from this noble discovery, it is most gratifying whether at the addition of another planet to our list, whether at the proving the correctness of the theory of universal gravitation, or in what view soever it must be considered as a splendid discovery, and the merit is chiefly due to theoretical astronomy. This discovery is perhaps the greatest triumph of astronomical science that has ever been recorded." End quote. If such things as criticism, experience, and comparative observation did not exist, the tone of exultation in which the above article indulges might be properly shared in by the astronomical student. But let the following extracts be carefully read, and it will be seen that such a tone is premature and unwarranted. Quote, Paris, September 15th, 1848. The only sittings of the Academy of late in which there was anything worth recording, and even this was not of a practical character, were those of the 29th ult and the 11th inst. On the former day, M. Babinet made a communication respecting that planet Neptune, which has been generally called M. Leverrier's planet. The discovering of it has, as it was said, been made by him from the theoretical deductions which astonished and delighted the scientific public. What M. Leverrier had inferred from the action on other planets of some body which ought to exist was verified, at least so it was thought at the time, by actual vision. Neptune was actually seen by other astronomers, and the honor of the theorist obtained additional luster. But it appears from a communication of M. Babinet that this is not the planet of M. Leverrier. He had placed his planet at a distance. These quotes were coming from Illustrated London Almanac for 1847. He had placed his planet at a distance from the Sun equal to 36 times the limit of the terrestrial orbit. Neptune revolves around at a distance equal to 30 times of these limits, which makes a difference of nearly 200 million of leagues. M. Leverrier had assigned to his planet a body equal to 38 times of that of the Earth. Neptune has only 1/3 of its volume. M. Leverrier had stated the revolutions of his planet round the Sun to take place in 217 years. Neptune performs its revolutions in 166 years. Thus then Neptune is not M. Leverrier's planet, and all his theory as regards to that planet falls to the ground. M. Leverrier may find another planet, but it will not answer the calculations which he had made for Neptune. In the sitting of the 14th, M. Leverrier noticed the communication of M. Babinet, and to a great extent admitted his own error. He complained indeed that much of what he said was taken in too absolute a sense, but he evinces much more candor than might have been expected from a disappointed explorer. M. Leverrier may console himself with the reflection that if he has not been so successful as he thought he had been, others might have been equally unsuccessful, and as he has still before him an immense field for the exercise of observation and calculation, we may hope that he will soon make some discovery which will remove the vexation of his present disappointment. End quote. As the data of Leverrier and Adams stand at present, there is a discrepancy between the predicted and the true distance, and in some other elements of the planet. It remains, therefore, for these or future astronomers to reconcile theory with fact, or perhaps, in the case of Uranus, to make the new planet the means of leading to yet greater discoveries. It would appear, for the most recent observations that the mass of Neptune, instead of being, as at first stated, 1/9,300th, as only 1/23,000th that of the Sun, whilst this periodic time is now given with a greater probability at 166 years, and its mean distance from the Sun nearly 30, Leverrier gave the mean distance from the Sun 36 times that of the Earth, and the period of revolution 217 years. Quote, May 14, 1847. A paper was read before the Royal Astronomical Society by Professor Shoemaker on the identity of planet Neptune, M. Leverrier's, with a star observed by M. Lalande in May 1795. End quote, end quote. This quote is coming from Times newspaper, Monday, September 8, 1848. Also Cosmos by Humboldt, page 75. Report of Royal Astronomical Society for February 11th, 1848. Number 4, Volume 8. Such mistakes as the above ought to at least make the advocates of the Newtonian theory less positive, and more ready to acknowledge that at best their system is but hypothetical, and must sooner or later give place to a philosophy the premises of which are demonstrable, and which is in all its details sequent and consistent. Pendulum experiments as proofs of Earth's motion. In the early part of the year 1851, the scientific journals and nearly all the newspapers published in Great Britain and on the continents of Europe and America were occupied in the recording and discussing of certain experiments, with the pendulum first made by M. Foucault of Paris, and the public were startled by the announcement that the results furnished a practical proof of the Earth's rotation. The subject was referred to in the Literary Gazette in the following words, quote, Everybody knows what is meant by a pendulum in its simplest form, a weight hanging by a thread to a fixed point. Such was the pendulum experimented upon long ago by Galileo, who discovered the well-known law of isochronous vibrations applicable to the same. The subject has since received a thorough examination, as well as theoretical as practical form, from mathematicians and engineers, and yet, strange to say, the most remarkable feature of the phenomenon has remained unobserved, and wholly unsuspected until within the last few weeks, when a young and promised French physicist, M. Foucault, who was induced by certain reflections to repeat Galileo's experiments in the cellar of his mother's house at Paris, succeeded in establishing the existence of a fact connected with it which gives an immediate and visible demonstration of the Earth's rotation. Suppose the pendulum already described to be set moving in a vertical plane from north to south. The plane in which it vibrates to ordinary observation would appear to be stationary. M. Foucault, however, has succeeded in showing that this is not the case, but that the plane itself slowly moving around the fixed point as a center in a direction contrary to the Earth's rotation, with the apparent heavens from east to west. His experiments have since been repeated in the Hall of Observatory under the superintendence of M. Arago, and fully confirmed. If a pointer be attached to the weight of a pendulum suspended by a long and fine wire, capable of turning round in all directions and nearly in contact with the floor of a room, the line which this pointer appears to trace on the ground, and which may easily be followed by a chalk mark, will be found to be slowly but visibly and constantly moving round, like the hand of a watch dial, and the least consideration will show that this ought to be the case, and will excite astonishment that so simple a consequence as this is of the most elementary laws of geometry and mechanics should so long have remained unobserved. Note, the subject has created a great sensation in the mathematical and physical circles of Paris. It is proposed to obtain permission from the government to carry on further observations by means of a pendulum suspended from the dome of the Pantheon, length of suspension being a desideratum in order to make the result visible on a larger scale and secure greater constancy and duration in the experiment. The time required for the performance of a complete revolution of the plane of vibration would be about 32 hours 8 minutes for the parallel of Paris, 30 hours 40 minutes for that of London, and at 30 degrees from the equator, exactly 48 hours. Certainly, anyone who should have proposed not many weeks back to prove the rotation of the Earth upon which we stand by means of direct experiment made upon its surface would have run the risk, with the mob of gentlemen who wrote upon mechanics, of being thought as mad, as if he were to have proposed reviving Bishop Wilkins's notable plan for going to the North American colonies in a few hours, by rising in a balloon from the Earth and gently floating in the air until the Earth in its diurnal rotation have turned the desired quarter towards the suspended aeronaut, whereupon as gently to descend. So necessary and wholesome is it occasionally to reconsider the apparently simplest and best established conclusions of science." End quote. The following is seen from Scotsman, which has always been distinguished for the accuracy of its scientific papers. The article bears the initials C.M., which will at once be recognized as those of Mr. Charles McLaurin, for many years the accomplished editor of that journal. Quote, "The beautiful experiment contrived by M. Foucault to demonstrate the rotation of the globe has deservedly excited universal interest. Note, a desire has always been felt that some method could be devised of rendering this rotation palpable to the senses. Even the illustrious Laplace participated in this feeling and has left it on record. Quote, although, he says, the rotation of the earth is now established with all the certainty which the physical sciences require, still a direct proof of that phenomenon ought to interest both geometricians and astronomers. No man ever knew the laws of the planetary motions better than Laplace, and before penning such a sentence, it is probable that he had turned the subject in his mind, and without discovering any process by which the object could be attained. But it does not follow that if he had applied the whole force of his genius to the task, he would have not succeeded. Be this as it may, here we have the problem solved by a man not probably possessing a tithe of his science or talent, and, what is very remarkable, after the discovery was made, it is found to be legitimately deducible from mathematical principles. And note, in this, as in many other cases, the fact comes first and takes us by surprise, after which we find that we had long been in possession of the principles from which it flowed, and that, with the clue we had in our hands, theory should have revealed the fact to us long before. M. Foucault's communication describing his experiments in the Compte Rendu of the Academy of Sciences for 3rd February 1851. His first experiments were made with a pendulum only 2 meters at 6 feet 6 1/4 inches in length, consisting of a steel wire from 6/10 to 11/10 of a millimeter in diameter. The millimeter is the 25th part of an inch, to the lower end of which was attached a polished brass ball weighing 5 kilograms or 11 English pounds. Note, a metallic point projecting below the ball and so directed as if formed a continuation of the suspension wire served as an index to mark the change of position more precisely. The pendulum hung from a steel plate in such a manner as to move freely in any vertical plane. To start the oscillatory movement without giving the ball to any bias, it was drawn to one side with a cord which held the ball by a loop. The cord was then burned, after which the loop fell off, and the vibrations, generally limited to an arc of 15 or 20 degrees, commenced. In 1 minute the ball had sensibly deviated from the original plane of vibration towards the observer's left. Afterwards he experimented on the observatory with a pendulum 11 meters or 30 feet long, and laterally at the Pantheon with one still longer. The advantage of a large pendulum as compared with a small one is that a longer time elapses before it comes to a state of rest, for machinery cannot be employed here as in a clock to continue the motion. The pendulum is suspended over the center of a circular table whose circumference is divided into the degrees and minutes. The vibrations are begun in the manner above described, and in a short time it is observed that the pendulum, instead of returning to the same point of the circle from which it started, has shifted to the left. If narrowly observed, the change in the plane of vibration, says M. Foucault, is perceptible in 1 minute and in a half an hour. Quote, "Il sente a you end quote, it is quite palpable.